We are beginning this session with a result where we are going to give up the restriction of positive definiteness of the covariance matrix sigma. So, our first result in this series is, well, we are continuing. So, this is our result 4 and we take that X is following a p-variate multivariate normal distribution with the mean vector mu and covariance matrix sigma, and as mentioned we have rank of sigma. Now, this is p dimensional. So, this is a p dimensional square matrix, but we take the rank of sigma as R, which is strictly less than p. So, this is the important relaxation that we are doing. This is the situation then the quadratic form X transpose Bx, say this is going to follow. Let us take a simplification here, when this can easily extend to the non-null vector also, but let us state it in this form, so that we consider simply X transpose instead of taking X minus mu transpose, and this as a result follows the standard chi-square distribution with R degrees of freedom, which is the rank of the sigma matrix, and the condition on the associated matrix B is that if B is a generalized inverse of sigma. So, you can see we have a situation of a singular multivariate normal distribution here. Sigma is positive semi-definite. So, as we had said in one of our earlier sessions, that the multivariate normal distribution is a singular multivariate normal distribution where the PDF does not exist because sigma inverse does not exist, and so obviously sigma inverse does not exist. So, what we are working with is a generalized inverse of sigma. Okay. So, let us go to the proof of this. So, we start with the proof of the result, and in the very beginning we consider some matrix P, let C a square matrix of same dimension as sigma, a non-singular matrix such that we have C sigma C transpose is the identity matrix of dimension R, rest of the blocks are all null matrices. Basically, what we are doing is we are considering a rank factorization and we are writing in this form. So, we have C sigma C transpose as I R, rest of them as null blocks, and then we consider the transformation. So, now we transform from X, we are going to Y, which is Cx. So, that we have X is nothing but C inverse Y, no problem in it because C is non-singular, and then what we see is by our earlier result we have Y, which is also a p-dimensional random vector. This follows a multivariate normal distribution, p-dimensional with mean vector C mu, and covariance matrix is C sigma C transpose. This is just the matrix that we have considered here. We have a partition of the covariance matrix as well in the form of I R null null null. So, basically now if I partition the Y matrix accordingly, so that the partitioned vectors are now giving me this covariance matrix, so that I have Y into Y1 and Y2. What I do is I can clearly see that the covariance of the first component is in here in the first block of the C sigma C transpose. So, basically this has been partitioned into R and P minus R components. So, this is the first one is an R dimensional vector, the next one is a P minus R, the residual is coming here, and so that I have, well, expectation of Y is nothing but I consider this as, well, I have started with X following normal P with mean null vector. So, obviously this is also both of them are null, mu 1 and mu 2, but what is happening is covariance of Y, and this is nothing but IR, right. So, this implies that the first component, the first subvector of dimension R, this is a multivariate normal distribution with mean vector is null and the covariance matrix is the identity matrix of dimension R. And what is happening to the second component? Well, this component, a p minus r dimensional vector, it has mean the null vector and the covariance matrix is the null matrix. So, what is happening is, in essential, I have this variable, this y2 random vector is actually a degenerate random vector and obviously degenerate at the origin, at the point 0. So, this is equal to the null vector with probability 1. We continue with this. So, let us have a look at the C sigma, that is the covariance matrix of the transformed variable y, C sigma C prime, which we are writing in this form now, and this is, as I said, that this is nothing but the covariance matrix of the new variable y. Now, here we are using the most common and the most popular definition of sigma of generalized inverse of a matrix. So, what we had started with, we had said that B is a generalized inverse of sigma. So, obviously, what we have is sigma, B sigma is nothing but sigma, since B is a G inverse of sigma, right. So, I can replace this sigma by this sigma B sigma and I have a C transpose at the end. Now, this is a little bit of manipulation, a little bit of trick here. I just import C transpose inverse here after sigma, then I write B, and then again what I bring in forcibly is C inverse, and then once again I write sigma C transpose. Now, there is no problem in doing so because I have C as non-singular. So, what I have done is I have basically imported this C transpose inverse, which is an identity matrix. So, no problem, I can insert it anywhere I like. Similarly, I have inserted this C transpose also, which is again an identity matrix of dimension P. So, no problem. Now, with this, first I am combining the first part, the first three matrices giving me I, R, and then the rest of it. What remains here is C transpose inverse B. Again I have, okay, what I will do here is, instead of writing, so that I can very conveniently again have a C sigma C transpose, I will write this is in this form. So, this is C inverse C, right, no problem in it, whether it is C inverse or C inverse C. So, I have a C inverse here, and then I have C sigma C transposes giving me again this matrix. I live at this stage and then I concentrate on the quadratic form that we had taken up, X transpose B X, and let us see what it is. Well, what was my transformation? The transformation was y is C x. So, basically x is nothing but C inverse y, and I use it here to get y transpose C transpose inverse B C inverse y. And now, I use the partitioned form of the random vector y and write this as, recall that y was partitioned into y1 and y2, and we have a transpose here. So, that this is y1 transpose augmented column wise, this is y2 transpose, and then I have C transpose inverse B C inverse, again I am writing y1 and y2. Now, what I do is, now after this I insert the matrix I R null null null. Now, this y2 we have already seen that this is nothing but this random vector is degenerate at 0 with probability 1. So, I can straight away write this is the null vector. Similarly, here also let me replace y2 by the null vector. Here also I am going to do the same thing. This is the null vector. What I am doing is I am bringing in this IR null null and null matrix here. It is making no difference because this is practically acting as the identity matrix as far as this vector is considered, and then I write this the rest of it sigma transpose inverse B C inverse, and then again bring in this same matrix and writing the vector at the end. Right. But put a transpose here does not make much of a difference. So, this is y1 transpose and we have this, and this has been shown to be equal to this matrix itself. So, simply I have this is getting replaced by the single matrix which has been proved in the earlier step, and then I have is coming up, which shows that this quadratic form is nothing but the sum of yi square I from 1 to r only. So, this is basically y1 transpose y1. Now, with y1 random vector r dimensional following multivariate normal with mean as the null vector and the covariance as IR, these are independent, and I can have the sum of squares following a central chi-square distribution with R degrees of freedom. So, I have X transpose Bx sigma, the covariance matrix of X was not positive definite, but it is just positive semi definite with rank equal to R, which was strictly less than the dimension P. And what was the only thing that we assumed here is something about this associated matrix B. We have taken this B as one generalized inverse of sigma. Okay, so, this proof is complete at this step. Now, we move to our next part of the results. The next group of results, now till now we have been considering either a linear form or a quadratic form in isolation and trying to show what their distribution is. Now, what we are going to do is we are going to consider two of them, that is two linear forms, a linear and a quadratic form, or two quadratic forms, and try to check their whether they are independently distributed or not, or basically talk about the condition when they will be independently distributed or not. This sort of independence, the establishing independence will be useful when we later go on to the inference part, and there we will see that to talk about to establish the test statistics, the distribution of the test statistics, independence of these quadratic forms are really important. Okay. So, our next result is result 5. We start with the simplest one. We say that X is multivariate normal with mean mu and covariance matrix sigma. We have two linear forms, say Ax and Bx. So, A and B did not be square matrices. This can be a Q by P rectangular matrix, whereas B can be an R by P rectangular matrix, and I will say that the two linear forms, sorry, this is not y but x, the same variable x, are independent if and only if A sigma B transpose is a null matrix. Proof is really simple. So, we first have a look. We have already established these preliminary things. So, which is that Ax is itself multivariate normal, q dimensional with A mu, A sigma A transpose as the covariance matrix, Bx the other linear form of X is another multivariate normal with mean B mu and covariance B sigma B transpose, and I am assuming suppose A sigma B transpose is in fact a null matrix. Now, what is covariance between Ax and Bx? Well, this is certainly A sigma B transpose, which has been assumed to be equal to a null matrix. Now, what is happening here? Let us see if I augmented Ax and Bx. What am I getting? Well, I am getting a r dimensional vector here, and this is q. We had taken A as, so Ax is q dimensional and Bx is actually r dimensional. So, the augmented one is q plus r dimensional, and this can be actually written in the form as A augmented B x, right. So, this is, I have a r plus q dimension p, and this is p dimensional. So, let us call this as some Cx, right. So, this Cx is now again going to follow a multivariate normal distribution with r plus q, and this mean is say C mu, and the variance, the covariance matrix is C sigma C transpose. But then what is C mu? What is the form of C mu? Well, it is nothing but A mu augmented B mu. And what is the form of C sigma C transpose? Well, it is A sigma A transpose in the first block, then it is A sigma B transpose of this here. So, it is B sigma B transpose A sigma, and then we have B sigma B transpose. Now, what we have here by our assumption is this off diagonal blocks as null matrices. So, that we have by our very special feature of multivariate normal, we say that these Ax and Bx are independent. So, this is something which we have used for the proof, and then we have the converse part. That is really simple. We have Ax and Bx are independent. Whether they are multivariate normal, I do not care about the distribution. I will always have covariance between Ax and Bx in that case as this null matrix, and this implies, because this covariance is nothing but A sigma B transpose, this is null. So, this is a simple proof of the independence between two linear forms of multivariate normal random vector Ax and Bx. Now, what we are going to consider is one linear form and one quadratic form, and see what is the condition for the independence between those two. Okay. So, our next result is, I take in a very general setup that this is following normal mu sigma with, we are again back to our usual important assumption that sigma is positive definite, and what I have is one quadratic form x transpose Ax and one linear form which is Bx simply. They are independent if and only if B sigma A, B is the associated matrix of the linear form and A is the associated matrix of the quadratic form, this is null. So, for the first part of the proof, that is, say, let us start with the sufficiency part, and we assume, suppose B sigma A is in fact null. So, what we do is we are considering a rank factorization of A. Now, A obviously is P by P, because X transpose A X is defined. Now, there is no need to consider A of full rank. So, I can have rank of A as R. So, I can consider a rank factorization of A, say, into L and L transpose, where L is of dimension P by R with rank of L equal to rank of A, which is R. So, basically it tells me that L is of full column rank. We are going to use this later. So, this is nothing but rank factorization of this matrix A, which is appearing in the quadratic form of X. Okay. So, now we have B sigma A, given that this is null. Well, this only implies that I am now going to use that A is nothing but L L transpose. So, this is null. So, what I do now is I bring in, I already have L L transpose, extra I write L transpose L inverse. This side still remains a null matrix. No problem in doing this. What I have brought in is L transpose L inverse, which exists because, as we have already said, that L is of full column rank. Not only this, this matrix L transpose L is R dimensional with its rank. Rank of L transpose L is nothing but equal to rank of L, which is equal to R. So, L transpose L is of full rank and its inverse exists. So, I bring it in here, the other side is still null. So, extra is this part, and let us see why we do this. How is it going to help us? It is almost immediate, because I see that I can get rid of these 4 matrices. So, that this is basically 2 matrices here combining L transpose L and L transpose L inverse, and I can write that B sigma L is the null matrix. Now, what is the advantage if I write B sigma L is null? I already had B sigma A is null, now I am establishing B sigma L is null. What I can do is I can use my earlier result and say in that case that covariance between 2 linear forms Bx and L transpose X, which is nothing but B sigma L, and which we have just now shown to be equal to a null matrix. This is equal to 0, and by our earlier result I immediately have Bx and L transpose X are independent. If Bx and L transpose X are independent, I might as well say that Bx and L transpose X, suppose this is some y, if I have X and Y are independent, I can very well say that X and Y transpose Y are also independent. So, that is exactly what I am doing here. I say that Bx and L transpose X transpose L transpose X, they are also independent. But what is this after all? This is nothing but our quadratic form X transpose A X, they are independent. By the way, what are the distributions? Well, I can see that this Bx also has a multivariate normal distribution. What about X transpose Ax? It has a non-central chi-square distribution. That does not matter. We can start with a general mu. If it is a null vector, then we will have a central chi-square independence between central chi-square and multivariate normal. Here it is incidentally a non-central chi-square. So, this is one part of the proof where we have assumed B sigma A as null matrix. Let us go to the other part. So, conversely, we are assuming Bx and X transpose Ax is the linear and the quadratic forms, they are independent. so I need not care about the distribution of these. I simply consider the covariance between these. One is random vector, this one is a random variable, and I consider covariance between Bx and x transpose Ax. I use the very definition of covariance between two random variables, and this is nothing but expectation of the first one Bx minus its expectation, what is B mu, and then it is the second one minus its expectation, where we have already seen what is the expectation of this quadratic form. This is nothing but mu transpose A mu minus trace of A sigma with a transpose. So, this is it. So, now what we are going to do is we consider this is B coming out, and we have B with x minus mu. So, just like we have this location shift here, it is now x minus mu, we try to do the same thing in this part also, in the other part. So, that now I write it forcibly as x minus mu transpose A x minus mu. When I do so, well, I have already included the x transpose A x and mu transpose A mu, but there are some extra cross product terms that I have introduced, and I must make adjustment for these, and hence that adjustment is giving me nothing but 2 x minus mu transpose with A mu, and I have the other term, that is a constant term remaining, which is trace of A sigma, right, this with a transpose. So, now what we are going to use is, now we have been given Bx and x transpose Ax are independent. Now, which also implies that we have, since Bx and x transpose Ax are independent, it is same as saying that Bx minus mu and x minus mu transpose A x minus mu note are also independent. And then what do I get from that covariance term? I am considering expectation of this Bx minus mu with this product. This is the first thing, joint expectation, that I am considering. Now, since these are independent, well, using the result that expectation of x y is expectation x times expectation y, I am doing just that, and note that as soon as I take expectation of the first part, I end up with a null vector. So, I have this as null here. Then what is happening in this part, in the second part? Well, I have twice, it is a plus sign, then the matrix of constants coming out. I have expectation x minus mu with x minus mu transpose, and I have another A mu. And what is happening with this part? Well, this is a constant part totally, and as soon as I take expectation, this is the only non-stochastic, this is the only stochastic part, and as I take expectation on this, this is going to be null. So, this part is null, and I had started with that these two are independent, this is equal to 0, this is given. So, what I have now is basically 2b, this is what, this is nothing but the covariance of x. So, this is basically, it is B sigma A mu, and this is equal to the null vector for all mu, because my given condition that Bx and x transpose Ax are independent. This is null for all mu in Rp, which will imply that the associated matrix has to be a null matrix. So, this is what we wanted to prove, that if the linear form and the quadratic form, they are independent, what I have is the associated matrices, a relationship involving them in this way. So, B is the associated matrix of the linear form, sigma is the covariance matrix of the random vector x, and A is the associated matrix of the quadratic form, and they together is a null matrix. Okay. So, this completes the proof. Next one is about the independence of two quadratic forms. So, we had started with the independence of two linear forms, next one was one linear and one quadratic, and now we come to the independence between two quadratic forms. Okay. So, this is result 7. We state this: x following normal P, start with the setup of mu I P and very conveniently use this setup in the general setup where we have x following a multivariate normal distribution with mean mu and the general covariance matrix sigma. So, first establish it for sigma equal to the identity matrix, the uncorrelated case. So, now then we have A and B are real symmetric idempotent matrices with some rank of A is say K1 and rank of B is K2, then the quadratic forms Q1, say the first one is x minus mu. We are deliberately taking this location shift to end up with central chi-square distribution. So, the first one is x minus mu transpose A, the first matrix coming into the picture, x transpose x minus mu transpose A x minus mu, and Q2 is the second one, x minus mu transpose B x minus mu are independently distributed if and only if the product of the two matrices A B is a null matrix. So, for the proof of this result, we start with, let us start with the necessity part, that is the only if part, and we suppose that the quadratic form. Incidentally, with the given condition, what are the distributions of these quadratic forms? Q1, which is x minus mu transpose A x minus mu, this will follow a central chi-square with rank of A as its degrees of freedom, and Q2, this is x minus mu transpose B x minus mu. This is also following a central chi-square with rank of B as its degrees of freedom, Q1 and Q2 independent. So, we start with this assumption and then complete the proof. So, we have two independently distributed chi-square variables. So, they are sum by the additive property of chi-square distribution, of independent chi-square distribution. This is also going to be a chi-square variable. So, that we have Q1 plus Q2, which is nothing but x minus mu transpose, and we have the matrices adding up A plus B x minus mu. This also follows a chi-square with K1 plus K2 as the degrees of freedom. Now, from our earlier result, we know that if this is a chi-square, then because that result was an if and only if result, so this is going to imply we have from here that A plus B is an idempotent matrix. Not only that, we also had seen there that rank of A plus B is actually equal to the degrees of freedom, that is rank of A plus rank of B in the special situation. So, A plus B is idempotent. Now, we use this idempotency of A plus B to establish what we have to show is that AB is a null matrix. So, if A plus B is idempotent, from the definition of idempotency, I have A plus B square is A plus B, which means that A square plus AB plus BA plus B square, this is A plus B. Now, note that there are many properties of A and B. They are symmetric and they are idempotent, right. So, I have A square is A and B square is B. So, this is cancelling out with these matrices and I am getting AB plus BA is a null matrix. The addition is a null matrix. So, what I do is, this is just one way of proving it. So, what I do is I pre-multiply by A, and this gives me A square B, which is again AB because A is idempotent, plus ABA, this is null obviously. At the next step, what I do is I post multiply by A again. So, what I get is, this implies what I have is A BA plus AB A square, which is ABA, and basically what I end up with is ABA is a null matrix. And using this step over here, this is going to imply that AB is also a null matrix because their sum is a null matrix. Okay, so I prove the necessary part of it, and then the sufficiency part. Conversely, here I am going to assume that AB is in fact a null matrix. What I consider at this stage is A times x minus mu. This is, now we know all these things, this is a p-variate multivariate normal with mean vector null because I already have made this shift here. And what is the covariance matrix? Well, the covariance matrix is nothing but A transpose, because the covariance matrix in this setup is actually the identity matrix. Now, A transpose is actually A times A because A is A transpose and A square is nothing but A. So, I end up with a p-variate normal 0 A. Similarly, B x minus mu also follows same dimension null vector and B as the covariance matrix. Now, what I have is, if I consider covariance between these two, that is A x minus mu and B x minus mu, what I get is, because the covariance matrix is nothing but an identity matrix, I have this as A B transpose, but B again being symmetric, this is A B. And now, this has been given to be equal to 0. Again, by our earlier argument or earlier result also where we have proved, we have these A x minus mu and B x minus mu, these are independent. Which immediately gives us what I do is I again take a transpose of this and multiply it with itself. That is, if I have x and y independent, I am considering that x transpose x and y transpose y are also independent. So, by that what I mean is I have A x minus mu, this transpose A of x minus mu, and B x minus mu transpose B times x minus mu. These are independent, and this is giving me x minus mu transpose. I again get A transpose A, which is A square, which is equal to A. So, I have A x minus mu and x minus mu transpose B x minus mu. These are in fact the two quadratic forms Q1 and Q2. These are independent if AB is a null matrix. So, this completes the other part of the proof also. As I had said, we had started with the simpler situation where we had assumed the covariance matrix to be an identity matrix. Now, we are going to go to the more general setup where we have the usual positive definite sigma matrix, but we are going to directly use the proof of this result to establish the result in that situation. We have just a small modification which is very obvious. So, this is now result 8. This says now I have x, a p-variate multivariate normal with mu sigma, and A, B as before are real symmetric idempotent matrices with rank of A as K1, rank of B as K2, then the same quadratic forms, then the quadratic forms Q1, the first one was with A. So, x minus mu transpose A x minus mu, and the next one, these are independent. You can guess that earlier where we had just the product of AB null matrix, here we have a sigma coming into the picture. So, that sigma gets inside and we have A sigma B is a null matrix. So, we are going to prove this one with the help of the case sigma equal to I that we have proved just now. For that, what we need to do is just a simple transformation, and I take some y, say. So, I am transforming from x to y, and I am saying that this is some C inverse x minus mu. What sort of C is going to help me is where sigma, this has been decomposed into C C transpose, and C is non-singular. Well, C is non-singular means, well, I have obviously taken sigma as positive definite and not positive semi-definite. Okay. So, if this is so, then what is the distribution of y? Well, then y in that case follows a p-variate normal with mean vector null and identity matrix of order p as the covariance matrix. I also have x minus mu. This is basically Cy, so that the first quadratic form Q1 in terms of y and c is nothing but, well, I am using that x minus mu is Cy. So, what I have is y transpose, c transpose, then A, and for x minus mu Cy. So, this is nothing but Q1, and this is under the given setup where A is idempotent with rank equal to k1, this is nothing but a central chi-square with k1 degrees of freedom, which incidentally is also rank of this matrix C transpose A C, because C being a non-singular matrix does not alter the rank of A when A is getting pre and post multiplied by C transpose and C. So, this is chi-square, central chi-square with k1 degrees of freedom. What about Q2? This is Y transpose C transpose B C Y, and this follows again, this because this is Q2 under the given setup where B is idempotent with rank equal to K2. So, this has to follow a central chi-square with K2 degrees of freedom, and I have in the situation where I have this sigma as identity matrix. So, now which I have exactly the same situation now, because moreover mu is also simplified to a null vector and the covariance matrix is in fact an identity matrix, the case I have proved earlier. So, by our earlier result, Q1 and Q2 are independent if and only if product of the associated matrices, that is a null matrix. So, the product of the associated matrices, the first one is C transpose A C and the next one is C transpose B C, this is null. Now, this result incidentally already proved, because here the random vector y has a setup with the identity matrix as the covariance matrix, and this has been proved for this case. So, this is, so what remains to prove is that this equal to null is equivalent to what we want to show to be null, that is A sigma B is null. So, this is a null matrix, means that I have C transpose A, C transpose is nothing but sigma, then I have B and C. This implies that I can, since C is non-singular, I can pre-multiply by C transpose inverse, post-multiply by C inverse to get A sigma B is, and each of these steps can be traced back. So, this is a null matrix is in fact equivalent to saying that A sigma B is a null matrix, because C inverse exists, and this is what we wanted to show. So, we are going to stop with this result in this type in the series of this type of results. The next topic that we are going to take up is sampling distribution from multivariate normal distribution, so that I can get I can get sufficient statistics for the parameters mu sigma and also obtain maximum likelihood estimators for the parameters mu sigma, and then henceforth we will talk about the distribution of those statistics, wherein we will encounter the Wishart distribution and the multivariate form of the t distribution, that is the Hoteling's t distribution.